But it will be first come, first served.
Yeah, so when you get the email, if you have a tight schedule, sign up as quickly as you can. Good. Okay. So what we're going to do over the next few lectures is talk really about the history of the universe itself. And so to place this in context, chronologically, what we're going to be talking about over the next few lectures is actually the first of the great origins that we're dealing with in this class, the origin and evolution of the universe itself. We didn't want to start the class with this, the chronologically first origins, because in many ways this is one of the harder ones to conceptually understand. And so the way we organize the material is to start with things that are a little bit more familiar, the Earth, the solar system, plate tectonics, stars, fusion, origin of the elements, origin of life, given the elements created in stars. And so this is kind of a chronological disconnect, right? We're going from 4.5 billion years ago in the origin of life back to 13.8 billion years ago and the origin of the universe. But conceptually, having built up the understanding of astronomy, geology, biology that we have now, it's much easier to tackle these questions about the origin of the universe. And that's really the reason for this organization of the material. So the questions that we're going to be dealing with are questions that have been asked for as long as we have any record of questions being asked. Cave paintings, you name it, right? Where does it all come from? Same questions. All that's changed in time is the answers to those questions and the sophistication of the answers that we have. And I'll end today's lecture by telling you a few of the where did it all come from questions that we still have, and we really don't have any clue what the answer is. So this question is still very much around, even though our parts of our understanding are much more sophisticated than they were 100 years ago, 1,000 years ago, 10,000 years ago, etc. And so really what we're going to be dealing with is the question of what is the history of the universe itself on billions of years timescales. How do the properties of the universe writ large change? This is the Big Bang model for the origin and evolution of the universe. As part of that, we will have to grapple with this dark stuff, dark matter and dark energy, that actually make up the majority of the stuff in the universe. Most of the material in the universe is not the atoms, neutrons, protons, electrons, the periodic table. It's other stuff that we call dark matter and dark energy. And then as part of thinking about the evolution of the universe itself, we're going to deal not only with what was the past, but a little bit about what the future might be. And this is really spread out over 3 different lectures, starting today with the expansion history of the universe, the idea of the Big Bang. Next time we'll talk about what the universe is actually made of, not the periodic table, but dark matter and dark energy is most of the stuff that the universe is made of. And then next week, we'll try to bring this all together and really understand, in this Big Bang model of the universe, how do we go from the beginning to all of the complicated things we see around us today, stars, planets, life, etc., kind of put together that entire history. And this kind of scientific subject of the history of the origin and evolution of the universe itself has its own name. This is called cosmology, sometimes confused with cosmetology, which is a very different branch of aesthetics, not science. So cosmology refers to really the idea of what is our origins on the scale of the universe as a whole. An example of a cosmological model that we've already seen is the Greek geocentric model. That was a very sophisticated cosmological model. The Earth was at the center. Everything else was kind of around, situated around the Earth, with the Earth at the center of the universe. This is a cosmological model. It is, we now know, a wrong cosmological model, but it's an example of a cosmological model. And so what we're going to do is talk about our current modern scientific understanding of cosmology. And so we're going to really address 4 different topics today. One is review briefly how we use light that we can detect here on Earth to unravel the history of the universe. Then talk about the expansion of the universe, why we think the universe is expanding, what does that even mean? In particular, then, talk about evidence for the Big Bang and what that itself means. And then at the end, I'll try to give you a sense of where the kind of frontiers of knowledge currently are. Where are the problems that people who are thinking about this, practicing scientists, what are they struggling with? This is an area of science that is progressing extraordinarily rapidly. I'm very confident that in your time at Berkeley, you will read newspaper articles about new breakthroughs in our understanding of the evolution of the universe as a whole. And so I'm going to just touch on a few of these areas where kind of our scientific understanding meets more speculative questions. That'll be the end. So I want to start by reminding you something we've emphasized multiple times already in the class, which is that astronomy is naturally a historical science. It takes light a certain amount of time to travel from one place to another, and that means when we look up at the sky and we look at distant objects, we inevitably see objects as they were in the past, because it takes light a certain amount of time to reach us. So this picture that I've shown several times of the Hubble Ultra Deep Field is basically a picture where the Hubble Space Telescope just stared at this one patch of sky for a very long time. This actually shows us galaxies, not as they are today, but galaxies as they were almost 12 billion years ago, when the light was emitted from those galaxies, and it's been traveling to us for 12 billion years to get to us today. Question?
Past observation and detecting patterns, do we have like a projection of what it looks like now?
Great question. So the question is, this is how that patch looked 12 billion years ago. What does that patch of the universe look like today? On average, we actually think that every big enough patch of the universe is on average similar to another big patch of the universe. So what we think is that this patch of the universe, which is incredibly far away from us, today, if we were sitting there, it would kind of look like things look like relatively close to us. And that's this notion that we'll come back to, that there is no special place in the universe. So what things look like today near us is on average what it looks like near any other galaxy at any other place in the universe. Great question. Okay, so this is one of the ways that we can use our observations of the sky to unravel the history of the universe, because light kind of for free gives us the fact that for very distant objects, we see them as they were in the past. But if we want to build up an actual dynamic view, not just a static view of how things look on the sky, but how things are actually moving around and changing, we need to have a way of actually measuring the speed of astronomical objects. And the way we do that is using something called the Doppler effect. So the Doppler effect is the idea that if you have a wave like light that's emitted by a moving object, then the wavelength of light that you detect depends on how fast the object is moving towards you or away from you. And this is illustrated schematically here. The blue source is a source of light that's either, if we're the observer here, this source of light is moving towards us. The light waves are scrunched together, so the wavelength of light is smaller, and we call that blue shifted because it shifted towards the shorter wavelengths in the electromagnetic spectrum, and those are the blue parts of the electromagnetic spectrum. On the other hand, if we're an observer sitting here, this source of light is moving away from us. That means the wavelengths that we see as the observer are stretched out a little bit, as shown in this movie, and we say that the light is redshifted. And the reason is, again, that longer wavelengths, larger distances between the peaks and valleys corresponds to longer wavelengths. Longer wavelengths are in the redder part of the electromagnetic spectrum. And so this is redshifted and this is blueshifted. And you're actually familiar with this from everyday experience. The same thing happens with sound. Oh. Interesting. That's a car horn. Initially, the car is coming towards you. The pitch is higher. As the car goes past you, the pitch, the way it sounds, the pitch goes down to lower frequencies. That's the Doppler effect. It happens to any wave, so it happens equally to sound that you can hear or light that you can see. Okay, that's irritating. But there's nothing special about light, right? This happens equally to sound and light. And so the way we do this in practice is we use these unique lines that every element produces, these unique emission and absorption lines, and we measure changes in the wavelengths of emission and absorption lines. So this is a spectrum of light. And the dark regions are the special wavelengths of light where hydrogen gas absorbs light. So the light passed through hydrogen gas has absorption at very special wavelengths. And those wavelengths where the absorption happens, the dark lines, less light absorption, those are unique to the hydrogen atom. But if this bunch of hydrogen gas is moving towards us, then the wavelengths of absorption are blue shifted, okay? So the light is shifted to the blue part of the electromagnetic spectrum. Sorry, that's down here. So this is the wavelength of light. This is shifted to the blue. This is shifted to the blue, to the left, the blue part of the electromagnetic spectrum. If the light is moving away from us, then the light is redshifted. It's shifted to the redder part of the electromagnetic spectrum. So we know where these wavelengths should be because we can measure the wavelengths of absorption by hydrogen and iron and carbon and nitrogen and oxygen and you name it in the laboratory on Earth. That tells us these, quote, rest wavelengths, the wavelengths in the laboratory on Earth. And then we can measure for any astronomical object, is it shifted to the red? Is it shifted to the blue? That tells us how fast is it moving, and is it moving towards us or is it moving away from us? And in particular, quantitatively, the formula we use, which we're not going to use in much detail in the class, I'll invoke it again later for one particular example, but the change in wavelength, the observed wavelength minus the rest wavelength divided by the west wavelength is exactly equal to the speed of the object divided by the speed of light. So we can use the observed wavelength and the known rest wavelengths from laboratory experiments to figure out the speed of astronomical objects. And so this is another piece of information that we can get about things that we see in the sky just by using observations on Earth. We not only can measure temperatures, etc., but we can measure the speeds of astronomical objects using the Doppler effect. Okay? Any questions about that? Okay. So now that we have a sense of how to measure the speeds of astronomical objects, I want to go on and tell you how we have actually inferred the expansion of the universe and what that actually means. So the last part of kind of building together our story about motions of objects in the universe is figuring out not only how fast things are moving, but where they are. We want to know not only is that distant galaxy moving towards us or away from us, how fast is it moving, but we actually want to know its distance so we can build up a full three-dimensional picture of where galaxies are and how fast they're moving. And this turns out actually to be extraordinarily hard. The major bottleneck in understanding kind of the scale of the universe, our place in it, how things are moving around us, has been figuring out the distances to astronomical objects, the distances to stars and galaxies and black holes and you name it. And the way we do it is actually we use very different observational techniques depending on how far things are from us. And that's what this diagram is trying to illustrate, that for things that are close to us in the solar system, we use one technique. We actually bounce radar waves off of planets, measure how long it takes radar waves to hit the planet and come back to us, and that allows us to measure the distances to planets in the solar system. To objects that are further away, that becomes impractical because it would take light centuries or thousands of years. Radar is a form of light. It's a radio wave, right? It would take radio waves thousands of years to come back, so that's impractical. So we use different techniques for more and more distant objects. And you don't need to know all of these techniques. What this is trying to convey is that there's an interwoven set of techniques that we use to measure the distances of astronomical objects. And the picture I want you to have, the analogy that I want you to have, is that this is similar to how we actually date rocks and fossils. So you talked in detail in section about how it's actually not possible to date directly by radioactive dating the ages of most fossils. What we do instead is we date certain layers of rock by radioactive dating, and then we use the principles of stratigraphy, that things that are deeper down are older than things that are closest to the surface, to put together a picture of the ages of fossils. We use a combination of absolute dating, radioactive dating, and relative dating, stratigraphy, to figure out the ages of layers of rocks and fossils. And our building up distances to astronomical objects is a similar interrelated set of arguments. Okay? And that's kind of the level that I want you to understand, is each of these techniques on its own is more complicated and more detailed than we're going to worry about. So let's now fast forward, many, many decades of difficult work where people have actually built together an understanding of the distances to astronomical objects. And let's ask the question in particular, what are the distances and speeds of galaxies that we observe around us? So this is a picture of galaxies relatively close to our own. This is our own galaxy, the Milky Way. This is our biggest neighboring galaxy, Andromeda. That's about 3 million light years away. The Milky Way is actually orbited by smaller galaxies, the Magellanic Clouds, these two. Even smaller galaxies are orbiting around our own. Similarly, Andromeda has little small galaxies orbiting around it. We talked about how about 4 billion years from now, Andromeda and the Milky Way are going to slam into each other in a big collision. And so when we look at objects that are relatively nearby, what we see is that the motions of objects are actually rather complicated. The Milky Way and Andromeda are orbiting around each other. Each of these galaxies is being orbited by smaller galaxies. Galaxies are slamming into each other, etc. And so on scales where you're looking at a few million light years, the motions of galaxies relative to each other are pretty complicated. Sometimes galaxies are coming towards each other, sometimes they're going away from each other, etc. What turns out to be truly remarkable is that if you look at galaxies that are even more distant, not a few million light years from us, but tens or hundreds of millions of light years from us, the motions of galaxies are dramatically simpler. It's not this complicated picture of things orbiting around each other. When you look at very distant galaxies, the picture of how galaxies are moving is simple, and it's that viewed from the Earth, all the distant galaxies that we can see in the sky are moving away from us. And observationally, what that means is that the light from very distant galaxies is all redshifted. It's shifted to the red part of the electromagnetic spectrum. That's the signature of things moving away from us. And this is actual modern astronomical data of the speed of distant galaxies as a function of distance. So notice this tick mark here is 300 million years. Each of these big tick marks is 300 million years. So we're not talking about 3 million years. We're talking about much larger distances now, hundreds of millions of years. On the scale of hundreds of millions of years, all the galaxies that we can see in the sky are moving away from us. Moreover, the further away the galaxies are from us, the faster they seem to be moving. And this discovery was made by Hubble in the late 1920s, and it's really one of the most important scientific discoveries of the 20th century. And this is the first signature of what we call the expansion of the universe, the fact that all distant galaxies are moving away from us. This is so important that it's given the name Hubble's law. And mathematically, the way we describe this is by saying that the speed of distant galaxies increases linearly with their distance. As the distance gets bigger, the speed that they're moving away from us goes up linearly with their distance. And there's a constant called Hubble's constant that relates distance and speed. And that measured constant is about 21 kilometers per second per million light years. So if you go a million light years away, on average, things are moving apart about 21 kilometers a second faster. So this is kind of the details, but this basic fact that all the galaxies, all the distant galaxies are moving away from us, that's really the big clue about the expansion of the universe. Yep?
So at the time that Hubble's constant was established, was there a general consensus of agreement in the community that was true?
So the question is, when Hubble made these measurements, these are not Hubble's measurements. These are modern measurements, actually done in part by Alex Filipenko's group here at Berkeley. When this was first made, there actually was general agreement that the basic observational result, that the light from distant galaxies is all redshifted, that was agreed upon. What people couldn't agree on and fought for decades about is the exact value of Hubble's constant. Hubble actually got it wrong by almost a factor of 10. And the reason is because it was very hard to measure the distances to distant objects. He could measure the speeds easily. The distances were hard to measure. Yep?
But Hubble did kind of imply that the universe was expanding and accelerating at the same rate.
So Hubble's results were rather quickly interpreted to mean that the universe was expanding. You also just said accelerating. That came much, much, much later, and we'll get to that next lecture. Yep?
Does Hubble's constant only apply for galaxies that are very far away?
Yes, very good. So this result, right, only applies if you're sufficiently far away. In the case of Andromeda and these little galaxies orbiting around us and orbiting around Andromeda, their motions are actually not dominated by the expansion of the universe. The motions of the nearby galaxies to the Milky Way are dominated by the gravity of the Milky Way, not the overall expansion of the universe itself. Excellent question. Yep?
So I heard that the universe doesn't really have like one point for it.
Yes.
But doesn't it follow that like if those things are more far away and where it's more concentrated is where it'll
Yeah, so the question is, doesn't this imply that there is a center where everything originated? And we'll come back to that in just a second. It'll be easier to address that explicitly in just a second. Yep?
I read that no matter what reference point you use of the universe, it seems that expansion. How is that possible?
Right. Excellent question. That's this slide. Was there another question? Yes. Right. So the question is, when does Hubble's law really start to apply? If I had points very close to us right here, Hubble's law wouldn't apply because the motion would be dominated by the gravity of the Milky Way. It's tens of millions of light years is where Hubble's law starts to really be valid. Distances between galaxies of tens of millions of light years. So Hubble's law and this observational result that everything is moving away from us, at first glance, flies in the face of everything we have learned since the Copernican revolution, because it really does seem to imply that we are at a special place. We, sitting here on galaxy A, look up at the night sky, and we see everything moving away from us, and that really, really sounds like there's something special about where we are, since everything wants to get away from there. Right? And this is not consistent with our Copernican ideas that there's nothing special about the Earth. It's not the center of the solar system. The sun is not at the center of the galaxy. And so there's two possible answers. One is that indeed our galaxy is at the center of the universe, or that it's not. We think the answer is the Copernican answer, that there actually is nothing special about our place in the universe. And the way to reconcile this is imagine you're sitting here on galaxy B and you make exactly the same measurements that we have made here. You look up at the night sky, you measure the distances to nearby galaxies, you measure their speeds. What do you measure? You measure exactly the same thing. If you're sitting here on this galaxy and you look up at the sky, you see that everything is moving away from you. So it's not that everything is moving away from us, it's that everything is moving away from everything else. And that's really how we understand the expansion of the universe. That's how we reconcile Hubble's observational result with the Copernican principle that there's nothing special about our position. And in fact, what is very important about the linear relationship between speed and distance, and we're not going to show this follows from a little bit of math that's beyond the math we're going to do in this class, but what is special about the linear relationship between speed and distance that Hubble found is that it predicts this result. That for a linear relationship between speed and distance, the expansion as viewed from galaxy A and galaxy B is the same. Everything is moving away from everything else. Yep?
As the universe gets older, does Hubble's constant get smaller because the things that like so that closer to the
So the question is, does Hubble's constant change in time? You may have noticed I put constant in quotes, and that's because it's actually not constant. It does change in time. And it changes in time for reasons we'll really get to next time, because the gravity of everything in the universe changes how fast things are moving. So yes, it's not strictly a constant, so this particular value that Hubble measured applies today. It didn't apply in the distant past. It won't apply in the distant future. Great question. So the picture that I want you to have is not of us having a privileged position and everything is expanding away from us, but it's something much more like this movie where all of the galaxies in this movie are moving away from each other. If you imagine you're sitting on this galaxy and you look up and you measure everything around you, everything is moving away from you. But if you sit on this galaxy and you look up at the night sky, everything is moving away from you. So this movie shows how the notion of sitting on our galaxy, measuring that everything is moving away from us if it's sufficiently distant, is perfectly compatible with the Copernican principle. And what it requires is really this idea that everything is expanding away from everything. And the way we actually think about this today, in the context of our modern understanding of the large-scale behavior of the universe, is that what's really happening is that space itself is expanding. It's not really correct in our modern understanding to say that galaxies are moving through space and that their speeds satisfy Hubble's law. Instead, we think of it more as a balloon that's stretched out and expanding, and that stretching out and expanding of space itself is what leads to this view of everything expanding away from everything else. And that's really the modern picture of the expansion of the universe that comes from Einstein's theory of gravity. What's his theory of general relativity? So special relativity is Einstein's theory that gave us equals mc squared. General relativity is Einstein's theory that gave us the expansion of the universe, black holes, things like that. Yep?
So in one of the earlier lectures, you mentioned that there's like one atom, like a cubic, like whatever. So does that mean that that is going to be like even emptier?
Yeah, so the question is, I mentioned before that on average, there's something like 1 atom per cubic meter of stuff in the universe. Incredibly rarefied. That's only true today. If the distance between objects is expanding, that means that in the future things will be further apart, but it also means that in the past things were closer together. And that fact that in the past things were closer together is really the key to our idea of the Big Bang origin of the universe that we'll get to in a few minutes. Yep? The question is, does it mean that gravity is weakening? It doesn't necessarily mean that gravity is weakening. What it means is that the gravity of everything in the universe is not strong enough, at least today, to stop everything from flying apart. So it does mean, in a sense, that gravity is kind of weak. But it doesn't imply that its gravity is getting weaker in time. So that's the distinction. And we'll come back to this question of will things continue to expand forever or not next time. Yep?
Space itself is expanding. Is space inside galaxies also?
The question is space inside galaxies expanding? That's a really good question that you're going to have to answer in 2 minutes. I'll come back to that. So, in fact, the way we visualize the redshift that Hubble discovered is slightly different in this view of the expanding universe. It's not just that distant objects are moving away from us fast, and so their light is redshifted. It's actually that as light travels from this distant galaxy to us, the universe itself is expanding as the light travels to us, and that expansion of the universe actually stretches the wavelength of light. And that stretching of the wavelength of light, making the wavelength of light longer, leads to the redshift of light. And so the way we think of it is not really, again, this is a subtle difference between the kind of Doppler effect that's relevant for sound here on Earth, and the redshift in an expanding universe. The subtle difference is that really the redshift is due to the expansion of space itself. And to illustrate why this difference is important, I want to actually show you some real astronomical observations that drive home this difference in interpretation. So this little red dot here, it doesn't look very interesting. That's actually a billion solar mass black hole gobbling up huge amounts of gas from its surroundings, producing one of the brightest sources of light that we see in the night sky. It's called a quasar, or a really boring name, active galactic nucleus. If you look at that position and you actually measure the light, the spectrum of light from that position, the spectrum, remember, is the light at different wavelengths. What you see is what I've shown here, brightness versus wavelength. So there's not much light at short wavelengths, and then you start to see light at longer wavelengths, and you see these peaks here and here. You see these specific peaks of light. So emission of light at very special wavelengths. This is actually emission due to hydrogen atoms in the gas that's swirling onto the black hole at the center of this galaxy. This line has a wavelength measured here on Earth of 121 nanometers. We can go into the laboratory, measure the wavelength of the different hydrogen lines, and the wavelength of this line of hydrogen is 121 nanometers measured on Earth. What is the wavelength that we actually detect from this place? Well, you can see it here. It's 880 nanometers. It's very different from 121. It's longer wavelength. It's redshifted. That's what redshift means when you actually measure the wavelength of one of these lines. It's not what you measure in the laboratory. It's longer than that. It's a longer wavelength. So let's use our handy observed wavelength minus rest wavelength gives us velocity to figure out the speed of this object relative to us. So you can do that. It's 880 minus 121 divided by 121. That gives us the speed. Observed wavelength is 880. Rest wavelength, what we measure in the lab, 120. And you get a crazy number, 7 times the speed of light. So that's problematic. We thought Einstein told us that nothing can move faster than the speed of light. So the right interpretation of this is that since the time that the light from that place was emitted, as it has traveled for billions and billions of years to us here on Earth, the universe itself has expanded in size by about a factor of 7. That expansion has stretched the wavelength of light from the emitted 121 nanometers to the measured 880 nanometers. And so this really is the kind of way, within the context of Einstein's theory of the expansion of the universe, of how we interpret these huge redshifts that we can see from astronomical objects. Okay? So this is kind of mind-boggling, right? A lot of this stuff about the expansion of the universe is some of the hardest conceptual stuff that we'll deal with in this class. Any questions about that? So now I want to come back to the question that I was asked, and I'm going to ask you. The universe is expanding, so are we expanding? Humans. The Earth. Is the Earth expanding? So think about this for a second. Talk to each other about it. This is not a trivial question at all, given what we've talked about so far. So I'm giving you 3 possible answers. Yes, the Earth is expanding, like in the picture. No, it's not. And then the waffly answer, yes, but so slow that we can't actually measure it. All right, any guesses? Go ahead. I see a few reds, perhaps more predominantly blues. So the right answer is, in fact, no. The Earth is not expanding. It's not even expanding imperceptibly slowly. And the reason for that is that the Earth is held together by its own gravity. So just like we talked about, that nearby galaxies to the Milky Way don't participate in Hubble's law, they move differently. That's because nearby objects to the Milky Way, their motion is dominated by the gravity of the Milky Way. For the Earth, the gravity of the Earth is actually holding the Earth together, and so the Earth is not participating in the broader expansion of the universe. So that's a subtle but important point that's often actually confused when you see popular descriptions of the expansion of the universe. So let me deal with a couple of those other tricky misconceptions. So we said that space itself is expanding is kind of the modern view of the expansion. Go ahead, question?
If the Milky Way's gravity makes things around us not expand, how are things elsewhere in the universe? Like if there was another large galaxy, how are those galaxies not stopping the rest from expanding?
So the question is, how do other large galaxies not stop things nearby them from expanding? And the answer is that other large galaxies affect things that are very near to them. So they do affect the motion of things very near to them, but they don't affect the motion of things that are far away. Great question. Yep?
If the matter in the universe is like everywhere, I don't think it is in like galaxies next to us, would never be able to expand.
Yeah, great question. So if the average density of stuff in the universe were the same as it is in our galaxy, would that change our picture of the expansion of the universe? You bet. We wouldn't be here today. The universe would have collapsed in on itself soon after the Big Bang. Would be a totally different story. Yes, good question. So the two, and we'll really come back to that issue next time. So the two big kind of confusing points about the expansion of the universe, one we've already dealt with, is that the universe is expanding. We think of that as space itself is expanding, but it doesn't mean that it's actually expanding into anything. And this is extraordinarily hard to get your mind around, so I'm just going to kind of put this up there and ask you to think about this. It's talked a little bit about in one of the readings this week, that we have this picture of an expanding balloon as kind of an analogy of the expansion of the universe. And what's misleading about that is that the balloon is expanding into something, but the expansion of the universe itself does not have to be, as far as we know, is not expanding into anything else. And the other point is one that was alluded to already, is that is there a center? And again, as far as we know, there is no center to the expansion of the universe. And it's true that if you rewind the expansion of the universe, all of the stuff gets closer and closer together, right? It's getting further apart. Rewind the clock, it gets closer and closer together. But that doesn't mean that there isn't stuff further away. And so there isn't, as far as we know, actually a center to the expansion. And again, the way to think about that is that the expansion is the same viewed from here, viewed from over here, viewed from over there. So there can't be a center, because the expansion is the same viewed from any position in the universe. There is no special place. There is no center to the expansion. So these are really some of the conceptually hard things to grapple with. And there's a reading this week that's entitled "The Misconceptions About the Big Bang," which specifically tries to deal and address with some of these conceptually difficult ideas about the expansion of the universe. So I particularly encourage you to take a look at that reading. Okay. So what we're going to turn to now is what do we mean by the Big Bang and what is the evidence for it? The Big Bang model basically takes very seriously the expansion of the universe. And it says if you take seriously the expansion of the universe, then you have to extrapolate backwards in time when things were much closer together. So extrapolating the expansion back in time, matter in the universe was much closer together, much denser, and it was much hotter. That's the basic idea of the Big Bang model. Rewind the clock, things are much closer together and much hotter. And in particular, if you extrapolate back far enough, about 13.8 billion years ago, what you find is that the conditions are so extreme, the matter is so dense and so hot, that it's hotter and denser than anything that we have any experience of. It's hotter than the center of the sun. It's hotter than the hottest conditions we can create in the Large Hadron Collider when we slam protons at the speed of light together, right? And so in particular, the conditions are so extreme as you rewind the clock. Things are so dense and so hot that physics, as we actually understand it today, breaks down. The laws of physics that we know do not apply at the extraordinarily dense and hot conditions that obtain when you rewind the clock 13.8 billion years ago, and things are closer together and hotter. And that's really what people mean by the universe is 13.8 billion years old. We have no idea whether there was something before this state of the universe. We can speculate about it. We'll come back to that at the end. But the part of the story that we understand with our current laws of physics are simply this part, that we can extrapolate back the expansion history of the universe, and that extrapolation, 13.8 billion years in the past, leads to conditions that are so extreme that the laws of physics as we know them break down. We don't know what happened before that time. Yep?
This extrapolation of expansion, so it's going backwards and then seeing like everything is compressed to a single point and then it extends.
So the question is the extrapolation backwards that everything was compressed together at a single point and then it expanded out? That's almost right. The part that's not right about that is the single point. Our current best guess, and this is another one of these difficult conceptual things, is that even 13.8 billion years ago, when things were extraordinarily dense and extraordinarily hot, the universe was infinitely big. It was not a single point. And that's kind of a corollary of this idea that there is no center. And we'll come back to that in just a second. So why do we take this idea seriously? This really sounds fanciful, right? We have this measurement of the expansion of the universe, but why should we take seriously this extrapolation so far back in time? And so what I want to go through are the two key pieces of evidence why we believe this extrapolation back in time. The Big Bang itself refers really to this period of time 13.8 billion years ago when the laws of physics as we know them break down. And so what I want to show you is the evidence we have that indeed we can observationally infer the conditions of the universe soon after this Big Bang, soon after this period of enormously high densities and temperatures. And there's two critical pieces of evidence for this. Two critical pieces of evidence why we take seriously the idea that in the distant past, the universe was much hotter and much denser. One is what's called the thermal background radiation, and the other is the fact that most of the normal matter in the universe is hydrogen and helium. And so I want to go through both of these lines of evidence. The first of these is one of the great triumphs of theoretical physicists, showing that theorists are actually more clever than experimentalists. So, after Hubble's discovery of the expansion of the universe, theorists started to take seriously this idea that if the universe is expanding, if you extrapolate back in time, things were denser and hotter in the distant past. And in the early 1940s, the prediction was made that an inevitable consequence of the expansion of the universe is that the universe should be filled with thermal radiation, this black body radiation, that is left over from the distant past when things were much denser and much hotter. And the basic argument went as follows. If the universe is expanding, then in the past, everything was much closer together and much hotter. And we know that very dense, very hot collections of gas produce thermal black body radiation. That's one of these fundamental laws of physics that we talked about when we talked about stars and planets, is that dense, hot objects produce this black body radiation, like the sun, like Jupiter, like human beings. We produce infrared black body radiation. And what people reasoned out is that if you extrapolate the expansion of the universe back in time, in the past, things were actually so close together, so dense, so hot, that the universe itself should be filled with this thermal black body radiation. That prediction was really made in kind of most detail in the late 1940s, and then it took the experimentalists, because they're a little slow, it took them about 20 years to catch up with the theorists, and this was confirmed in the mid-1960s. And this is this observation that I told you near the beginning of the class was one of the most important and yet most boring observations of the night sky, which is that if you look up at the night sky with a microwave telescope, you see that the sky in every direction is filled with a uniform glow of radio waves. Microwaves are a kind of light that's in the radio part of the electromagnetic spectrum. Just to remind you, this projection is like the following projection of the Earth. It's a projection of the sphere, the entire night sky that we can see, projected onto a two-dimensional plane. Up, down, right, projected onto the top and bottom of the image, North Pole, South Pole, etc. And so this is intended to show that every direction on the sky is filled with this glow of microwave radiation. In fact, in the old days, TVs, if you tuned your TV to a frequency where there wasn't actually a TV station, so there was just fuzz, okay, static, about 1% of the static on a TV was actually the leftover microwave glow from the Big Bang. Most of it was other sources of static, but about 1% of that was this thermal background radiation, or what's also called the cosmic microwave background. Microwave, because that's the part of the electromagnetic spectrum that we see it in today. This radiation is almost perfectly thermal radiation. We talked about, when we talked about thermal radiation, that thermal radiation has this property that if you know the temperature, you can uniquely specify the amount of light, or the brightness, as a function of the wavelength of light, or the frequency of light. So this shows the measured distribution of light as a function of frequency for the microwave background radiation, and the black line is this thermal black body prediction for a temperature of negative 450.8 degrees Fahrenheit, which is 2.73 degrees Kelvin. So it's almost perfect. It's one of the best black bodies we have, is the actual night sky in microwave light. So that's the kind of observational confirmation of this idea that the expansion of the universe rewound back in time should reveal itself through this leftover thermal radiation, left over from when the universe was much denser and much hotter. We think the way this radiation was produced was that, and this is a schematic illustration, this is hard to illustrate schematically, so I'm trying to illustrate it schematically as follows. When the universe was much denser and hotter, there was lots of stuff for light to bounce into, and so the thermal radiation that filled the universe kind of bounced around like this. As the universe expanded, cooled, and got less dense, eventually things reached a point where the thermal radiation that filled the universe could travel on straight lines across the entire universe. So on average, as the thermal radiation travels through the universe today, it doesn't run into any atom or molecule. In the very early universe, though, things were so dense and hot that it was bouncing around and running into things. And so there was a transition about 380,000 years after the Big Bang. Was this transition from the thermal radiation bouncing around to the thermal radiation traveling on straight lines? And that happened when the universe had a temperature of about 3,000 degrees, when the thermal radiation had a temperature of about 3,000 degrees. We measure today a temperature of about 3 degrees, and that difference between the thermal radiation when it was emitted, when it started traveling on straight lines of 3,000 degrees, and the thermal radiation whose temperature we measure today of about 3 degrees, that tells us that since the time that the thermal radiation was produced, the universe has expanded by about a factor of 1,000, redshifting from 3,000 degrees to 3 degrees. And the reason I'm emphasizing this kind of understanding of the thermal radiation is that this is actually the most important probe we have of the early universe. We'll talk about it a lot next lecture and the following lecture. This is our most quantitative probe of the state of the universe in its early history, is through observations of this thermal background microwave radiation. Okay. So now a question for you. If the universe became transparent to this thermal radiation when the temperature was about 3,000 degrees, that means that's when the thermal radiation stopped bouncing around and started to travel on straight lines. It, on average, didn't run into an electron or an atom. That was about 380,000 years after the Big Bang. What part of the electromagnetic spectrum was the thermal background radiation in at that time? Today, we look up at the sky and we measure the thermal background radiation as being in the microwave part of the electromagnetic spectrum. But what part of the electromagnetic spectrum was it in when it was produced? Okay. Is it the visible part of the electromagnetic spectrum, infrared, radio, or ultraviolet? So take a second, talk to each other about that. Okay, I see some greens. So before you make green your final answer, hint, hint, let me remind you of something. What's the surface temperature of the sun? 6,000. Where does the sun emit most of its light? What part of the electromagnetic spectrum? The visible, hence our eyes seeing in the visible. This is colder than the visible by a little bit. Sorry, this is colder than 6,000 by a little bit. So what should the wavelength be relative to the visible? Should be a little longer than the visible. What's a little longer than the visible? Right. Infrared. So there's a couple of ways to think about it. I think the easiest way to think about that is to remember 6,000 is visible. 3,000, that means, is a little bit longer wavelength than visible because colder stuff emits at somewhat longer wavelengths. A little bit longer wavelengths than visible is the infrared part of the electromagnetic spectrum. And so what has happened in the almost 13.8 billion years since the cosmic microwave radiation was emitted? The universe has expanded tremendously in size. And so the microwave background has shifted from the infrared part of the electromagnetic spectrum where it was produced. It has shifted in wavelength by almost a factor of 1,000 into the radio part of the electromagnetic spectrum, the microwave part of the electromagnetic spectrum, where it is today. So any questions about that? Okay, so what I want to do now is talk about our second key observational clue about the very early history of the universe, which is the fact that most elements in the periodic table, most of the normal matter in the universe is actually hydrogen and helium. So this gets back to this point that I made, that if we extrapolate the expansion of the universe back in time, we find that in the very distant past, things were so dense and so hot that matter was broken down into its most fundamental constituents. And so I want to explain a little more why this happens. So we've actually dealt with kind of the opposite of this process so far. What we've talked about when we talked about fusion in stars is how you go from light elements to building heavier and heavier elements. Fusion takes protons, combines them to form helium. And you need high temperatures for that to happen. Tens of millions or even hundreds of millions of degrees. And the reason you need those high temperatures, to remind you, is because the two positively charged protons have this electric force between them, and the high temperatures give you high speeds, which allow you to overcome the electric force and allows the nuclear force to become important and allows fusion to proceed. But if you go to even higher temperatures, what happens is the protons are whizzing around with so much energy that every time a proton runs into, say, a helium nucleus, the proton has enough energy to completely blow the helium nucleus apart. It has more energy in its energy of motion than the energy holding the helium nucleus together. So at really high temperatures, you don't actually have fusion. What you have is matter gets broken down into its most basic constituents. And that's really the reason for this argument here, is that as you go back in time, you don't have hydrogen and helium anymore. Things get broken down into just protons and neutrons. If you go even further back in time, you don't even have protons and neutrons. You have matter broken down into its even more fundamental constituents, quarks or strings or whatever the most fundamental constituent of matter is. So if we imagine a kind of schematic diagram of the nature of matter in the universe, time is going forward here, temperature is going down as the universe expands. The really, 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 really misleading thing about this diagram that you should not take seriously and not believe is what? That it started at a point and that there was a center, exactly. It's very hard to depict this, and so people typically depict things like this, but this is actually a little misleading. So in the very earliest phases of the expansion of the universe, extrapolating way back in time, we think that the nature of matter was simply a soup of whatever the most fundamental particles is. I use soup, right, kind of metaphorically, not literally. Just a collection of whatever the most fundamental constituents of matter are. Strings, quarks, electrons, whatever. And as time goes on, as things cool, you're able to start to form the normal matter that we're more familiar with. When the temperature is about 1 billion degrees, which is about a microsecond after the Big Bang, protons and neutrons can form. Before that time, there's so much energy and everything whizzing around that the collisions destroy protons and neutrons, and they break protons and neutrons into their more fundamental constituents, things called quarks. So, just to be clear, we tend to define t equals 0, the beginning, as the time when our understanding breaks down. The time when we extrapolate far back that matter is broken down into its most fundamental constituents, the laws of physics as we know them break down. Just because we call that t equals 0 doesn't mean there wasn't something before then. It just means we don't know what the nature of matter was before that time. So that's what I mean by t equals 0. So neutrons and protons form after about a microsecond. Question? Yep. Great question. Could there be multiple universes expanding simultaneously? Absolutely. That's a very popular area of research today. We'll come back to that in just a second. After about 3 minutes, things have cooled to tens of millions of degrees where fusion can happen, and that's when hydrogen and helium start to form. Question? Yep. Great question. So the question is, can we get this cosmic soup in the centers of black holes? Yes, at the centers of black holes, you have a similar situation where matter gets to extraordinarily high temperatures and densities, and it's broken down into its most fundamental form. That's the one other place in the universe where we know this happens. Great question. Yes. So 3 minutes after the Big Bang, you start to form hydrogen and helium. About 380,000 years after the Big Bang, the electrons that were flying around become bound to atoms, and so you actually start to form neutral atoms. Before this time, the electrons were just whizzing around free, like at the center of the sun, but about 380,000 years after the Big Bang, the electrons become bound to atoms, and that's actually why the universe becomes transparent. The universe becomes transparent to the thermal radiation when the temperature drops enough that the electrons become bound to atoms. And so the amazing prediction that has been made and confirmed observationally is if you take seriously this model of the expansion of the universe, you can work out what element should have been produced 3 minutes after the Big Bang when the temperatures were right for fusion to happen. And what you predict is that the universe should be mostly hydrogen and helium with a little bit of isotopes, deuterium, which is hydrogen with an extra neutron, helium, with is hydrogen with one less neutron, 1 neutron instead of 2 neutrons, and a little bit of lithium. And the fusion in the early universe stops at this point. It doesn't proceed to heavier elements because there isn't enough time. the universe is expanding and cooling so quickly that there's only time to fuse these light elements. There's not time to fuse heavier elements. And so this is an amazing prediction of the Big Bang model, that the universe should be mostly made of these light elements. And indeed, the Big Bang model makes very specific predictions for how much hydrogen, deuterium, helium-3, helium-4, and lithium there should be. And those all seem to be reasonably consistent with the observations we make. And that's a remarkable prediction, because it could have been that the model predicted 4 of the abundances right and 1 wrong, and that would have falsified the model. And so this is really, I think, an astonishing observational result, that just knowing that stars are mostly made of hydrogen and helium actually tells us the state of the universe 3 minutes after the Big Bang. And that really completes, in many ways, our understanding of the origin of the elements in the periodic table. The light elements, hydrogen, helium, and lithium, are formed in the first 3 minutes of the expanding universe. Basically, the rest of the elements in the periodic table are formed by stellar processes, fusion, supernovae, etc. And then there's a few elements that are only formed in laboratory experiments. Yep?
This is a bit of a tangent that I don't want to take too much time. How seriously is the mini universe theorem taken? Is there a lot of evidence for it?
Yeah. So the question is, how seriously do people take many universes? I'm going to get to that in just 1 second. Yep. Okay. So these then are the 2 key observational probes, the 2 key reasons why we take extraordinarily seriously this idea that if you rewind the expansion of the universe, you predict that in the distant past things were much denser and much hotter. The thermal background radiation was emitted 380,000 years after the Big Bang. It contains information, actually, about even earlier times, as we'll talk a little bit about next time. The light elements, the fact that the universe is mostly hydrogen and helium, tells us the conditions a few minutes after the Big Bang. And these are really the 2 pillars, the 2 primary observational lines of evidence for the Big Bang model. So as I already alluded to, one of the things that's really tricky to think about when you think about the Big Bang is that it's not an explosion at a place. As far as we know, there is no center. And as far as we can tell, the universe was actually extraordinarily large, possibly even infinitely large, even at the time of the Big Bang. Even when things were extraordinarily hot and extraordinarily dense, it's not that things were at a point. There was matter still filling an extraordinarily large amount of space. And so in the last few minutes, I want to mention just a few of the puzzles that this still raises and that we're struggling with. And that really are now kind of at the forefront of our thinking about the early history of the universe. And one of them is actually related to this idea of there is no center, the universe might actually be infinitely big. So when we look up at the sky, because 13.8 billion years ago, matter was extraordinarily dense and extraordinarily hot, and things were incredibly close together, that means that we can only see a finite size of the universe. There's only a finite size over which light has been able to travel in the 13.8 billion years since the Big Bang. And we call that the visible universe. This patch of the universe was indeed a very small region, smaller than an atom at the Big Bang, an extraordinarily dense, extraordinarily hot, tiny little volume of space. But that doesn't mean that the entire universe was an extraordinarily small region. there's no reason to think that there wasn't other stuff out there that we just can't see. This is the region we can see since the Big Bang, but there could very well be stuff that's still out there. And the question is, and people are really struggling with this, is if that's true, how can you possibly approach that as a scientific question? What experiment can you possibly make that would give you information about the state of the universe way out here, given that light hasn't even been able to travel from there to us in the time since the Big Bang? And we don't know if that question will ever be answerable, or if this will really always be speculation and really more in the realm of philosophy than in the realm of science. And that's something that there's actually a lot of active research. So a related question, instead of thinking about space, that there could be stuff further away than we can see since the Big Bang, let's think about time. So we have this very nice progression of events. Superfundamental particles, protons and neutrons form. Hydrogen, helium, lithium form by fusion. Atoms form 380,000 years after the Big Bang. What we'll do in a few lectures is keep going forward in time. Galaxies form, planets form, the Earth form, life form, dinosaurs form, and eventually humans form. Okay? But what if instead we try to go even further back in time? What happened before this phase of the universe being a soup of fundamental particles? And we don't know. But there's an extremely attractive idea that actually has a decent amount of observational support. The observational support is subtle to describe, so I'm largely not going to describe it. If you're interested, I'm happy to talk about it afterwards or in office hours. But it is the idea that very, very soon after the Big Bang, at this ridiculously, absurdly short amount of time after the Big Bang, 10 to the minus 36 seconds, which is an extraordinarily short amount of time relative to even the short amounts of time we've been talking about, microseconds and minutes, the universe may have actually undergone a period of very rapid expansion that stretched the distances between objects out tremendously quickly. And this idea is attractive because it solves serious problems that exist with simpler Big Bang models that don't include this very rapid early expansion of the universe. And this rapid phase of expansion is actually believed to produce, ultimately, the seeds that ultimately become you and me, the sun, the earth, the galaxy, etc. Small differences in one part of the universe to another were created in this early phase of expansion and develop over time into all of the complicated structure we see around us. So this phase is in many ways really the most active area where people are trying to push back our understanding of the expansion of the universe. But what if we're bold? What if we're not satisfied with 10 to minus 36 seconds? That seems like a really long time. Let's try to go even further back in the expansion of the universe. What was there then? We don't know. There's a bunch of ideas. One idea is that there was nothing. No space, no time, nothing. And then the universe just came to be at some point and started expanding, and then we can sensibly talk about it. But we really can't sensibly talk about what there was before this time. Okay, I find that to be kind of a not very attractive answer. It could turn out to be right. The idea that has the most attraction these days is the idea that, in fact, our universe is just part of a much larger structure. Within that much larger structure, there are regions that every once in a while, for reasons we don't fully understand, start undergoing expansion, producing little big bangs, kind of filling up this much larger universe. And this is the kind of general idea that our visible universe, illustrated, say, in this little bubble with its galaxies, is part of a much larger construct, often called the multiverse or multi-universe, where there are other regions that are undergoing their own expansion, and maybe even these other parts of the universe have very different laws of physics. And this idea is attractive, and I think the challenge that we're facing now as a scientific community is really figuring out how to test this. These are regions we can't communicate with, with information traveling at the speed of light, so how can we test this idea? And in many ways, this is kind of the frontier now of our understanding of the expansion of the universe, is pushing our knowledge back to earlier times and these much larger distances. Okay, so I'll stop there. Feel free to come up and ask questions. Next time, we'll talk about why we actually think we're so insignificant and only make up a few % of the stuff in the universe.